Okay, so uh, hello. Yes, so yes, start with the question number 41. We have covered up to 40. Now, question is, see, these are the questions from previous year. First is from 2009, All India 2009. How would you account for the following? Question is, many of the transition elements and their compounds can act as good catalysts. So, what is the reason? Yes, beta. Why many of the transition elements and their compounds act as good catalysts? So, reason is because most of the transition elements and their compounds have unpaired electrons, have partially filled d orbitals, they have variable oxidation states, can provide surface area, and can form complexes. So these are the criteria for an element or compound to be act as a good catalyst. So all of these conditions are satisfied by transition elements and their compounds. That's why they act as good catalysts. What about second? The metallic radii of the third series of transition elements are virtually the same as that of the corresponding members of the second series. Yes, beta. What is the reason for it? I have not written answers of those questions we have covered in the previous lectures. Yes. Yes, beta. What is the reason? Simple reason is due to lengthenoid contraction. Second and third transition series have almost same size like zirconium and hafnium, niobium and tantalum. They have almost same size. So what we write? Due to lengthenoid contraction. That is the reason. Next, there is a greater range of oxidation states among the actinoids than among the lanthanoids. So what is the reason? Reason is there is very small energy difference in 7s, 6d and 5f orbitals. Therefore, all of them can participate in bonding, and these are the orbitals in actinoids. We will write in the start that in actinoids there is a small energy difference, very small energy difference in 7s, 6d and 5f orbitals, and therefore all of them can participate in bonding. Okay, and that's why they show large, greater range of oxidation states as compared to that of lanthanoids in 6s, 5d and 4f. That is the reason. Next, the atomic radii of the metals of, again same question, third series of transition, this is from the late 2010. The atomic radii of the metals of the third series of transition elements are virtually the same as that of the corresponding members of the second series. So what is the reason? Yes, beta. What is the reason? Yes, Pranay. What is the reason? Why the atomic radii of the metals of third series of transition elements are virtually the same as that of the corresponding members of the second series? So it is due to, it is again due to lanthanoid contraction. We did this question just now. Next, the E naught value of Mn3 plus to Mn2 plus couple is much more positive than that of Cr3 plus to Cr2 plus or Fe3 plus to Fe2 plus. So just see, if you see Mn3 plus, it is 3D4, but Mn2 plus is 3D5, exactly half filled. So more stable, and that's why it is easy to form Mn3 plus to Mn2 plus, and because of this E naught value of Mn3 plus to Mn2 plus is more positive. Now come to Cr3 plus and Cr2 plus. So Cr, 3D5 4s1, Cr3 plus is 3D3. So in aqueous solution, it exists as T2G3, means more stable. But Cr2 plus, it is 3D4, that is obviously less stable. This one is more stable because exactly half filled T2G orbital, it becomes T2G3 and Eg1. So more stable to less stable, obviously it is, means not as easy as Mn3 plus to Mn2 plus, because in this case less stable to more stable ion is formed. Same is the case with Fe3 plus. Fe3 plus is 3D5, exactly half filled, more stable, and Fe2 plus, it is 3D6, that is less stable. So more stable to less stable. That's why E naught value of Fe3 plus to Fe2 plus is also not as, means E naught value is negative. Okay, but Mn3 plus to Mn2 plus, it is easiest one because less stable to more stable ion is formed. In both the cases, in this, more stable ion is converted into less stable ion, and that is not as easy as the first one. There it is difficult. Next, highest oxidation state of a metal is exhibited in its oxide and fluoride. Why? Due to their high electronegativity and small size. Okay. Yes. So This one, highest oxidation state of metal, it is exhibited in its oxide or ferrite because of high electronegativity of the element and at the same time their small size. And out of oxygen and fluorine, which one is superior? Out of oxygen and fluorine, very good. Oxygen is superior because it has ability to form multiple bond. It has ability to form multiple bond. Great. Next question. Complete the following. First is MnO4 negative plus C2O4 2 negative plus H plus. So in this case, first of all, MnO4 negative gives Mn2 plus in acidic medium. Add H2O to the side deficient of oxygen and double number of H plus ion to the opposite side. So on the left side there is 7 positive, on the right side 2 positive. So we add 5 electron. Now C2O4 2 negative, that is giving 2 CO2 plus 2 electron. So just cancel out the electrons by equalizing them. 5 multiplied by 2, 2 multiplied by 5. So 10 electrons on the left side, 10 electrons on the right side. So electrons are cancelled out. So it becomes 2 MnO4 negative, 5 C2O4 2 negative plus 16 H plus to give 2 Mn2 plus 10 CO2 plus 8 H2O. So this is the balanced chemical equation for the first one. Now KMnO4 on heating. Yes, beta. KMnO4 on heating, what it gives? KMnO4 on heating. When we heat KMnO4, it will give KMnO4 on heating at 513 Kelvin. It is disproportionate to give K2MnO4 plus MnO2 plus O2. So see, is it balanced? 2 K 2 Mn, 8 oxygen, 4 plus 2, 6 plus 2, 8 oxygen. Okay. So say KMnO4 on heating undergoes disproportionation. Say in KMnO4 it is plus 7, in K2MnO4 it is plus 6, and in MnO2 it is plus 4. Next question. Cr2O7 2 negative. In acidic medium it gives Cr3 plus. So balance the atoms other than hydrogen and oxygen. So it is chromium, 2 chromium on both sides. Add H2O to the side deficient of oxygen. Double number of H plus ion to the opposite side. Total 12 positive on the left side, 6 positive on the right side. So we add 6 electrons. Now H2S. So H2S gives sulfur. It is oxidized to sulfur plus 2H plus 2 electrons. So it is multiplied by 3. So electrons are balanced now. So what would we get? We get Cr2O7 2 negative plus 3 H2S plus 14 H plus on the left side, 6 H plus on the right side. So 8 H plus, 2 Cr3 plus, 3 sulfur and 7 H2O. That's it. See, is it balanced? Yes. 2 negative, 8 positive. So total 6 positive on the left side, 2 3s are 6 positive on the right side. That's it. So it is balanced. So first, second, and third. These are the complete balanced chemical equations. Next, many of the transition elements are known to form interstitial compound. It is the okay. So many of the transition elements are known to form interstitial compound. This question we okay. So see, many of the transition elements are known. What are interstitial compounds? Yes, beta. What are interstitial compounds? See, this is the metallic lattice. So if small atoms are trapped in these sites, interstitial sites, so these are called interstitial compounds. So see, transition elements, metals, they form large number of interstitial compounds in which small atoms such as hydrogen, carbon, boron, and nitrogen occupy the empty spaces in the crystal lattices of transition elements. Okay, so that's why we can say many of the transition elements are known to form interstitial compounds. So we say that in the crystal lattice of transition elements, small atoms like hydrogen, carbon, boron, nitrogen can be occupied in the empty spaces or interstitial spaces in the crystal lattice. That's why they can form interstitial compounds. Next is next question. Many of the transition elements, sorry, metallic radii of the third series of transition metals are virtually the same as that of the corresponding group members of the second series. So what is the reason? Yes, that is due to lengthened contraction. No need to write now because it is repeated, I think, 3 to 4 times. Next, lanthanoids form primarily +3 ions, while the actinoids usually have a higher oxidation states in their compounds, +4 or even +4 or even +6. So, what is the reason? This is again simple question. Yes, small energy difference between 7s, 6d and 5f. 5f, 6d and 7f. There is a very small energy difference between them. Therefore, all of them can participate in bonding. Okay, great. What about this? With the same D configuration, Cr2 plus is a reducing agent, while Mn3 plus is an oxidizing agent. So, what is the reason? Yes, beta. What is the reason? See, reducing means what? Reducing means which can lose electron. So say if Cr3 plus Cr3 plus, see, so if you see the electronic configuration of Cr3 plus, it is 3d 3. Cr3 plus is 3d3. That means it is T2G3. that is more stable as it is exactly half filled. Now, oxidizing agent means which can gain electron. So when it gain one electron, it become Mn2 plus, that is 3d5. Again, it is exactly half filled, T2G3 Eg2. So you can write that what you write that Cr3 plus is more stable, and that's why Cr2 plus can easily lose one electron to form Cr3 plus. And in case of Mn3 plus, you can write that Mn2 plus is exactly half filled again, which is more stable. That's why Mn3 plus is acting as oxidizing agent. Because to lose electron by Mn3 plus, it become Mn4 plus, that is also T2G3. But in that case, huge amount of energy is required, because 3 plus to 4 plus, it is fourth ionization energy, and that is very, very high. That's why after after gaining one electron, it has exactly half filled configuration, and that's why we can say that Cr2 plus is a reducing agent and Mn3 plus is an oxidizing agent. Next, actinoids exhibit a large number of oxidation states than the corresponding members of lanthanoid. Again, same reason, due to very small energy difference, due to very small energy difference between due to very small energy difference, 7s, 5d and 7s, 6d and 5f. Most of the transition metal ions exhibit characteristic in colors in aqueous solution, because they have partially filled d orbitals. They have partially filled d orbital, so they can exhibit dd transition, and that's why they are colored. Next, explain the following observations giving an appropriate reason for each. Enthalpies of atomization of transition elements are quite high. Enthalpies of atomization of transition elements are quite high. The reason is that transition elements has large number of unpaired electrons, and that's why they have strong metallic bonding. And due to this strong metallic bonding, their enthalpies of atomization are quite high. Got it, beta? Next is there occurs much more frequent metal-metal bonding in compounds of heavy transition elements. So in heavy transition elements, there are more loosely held electrons, and that's why they can participate in bonding much more frequently than in the lower than in case of lower members, and that's why metal bonding is more frequent, because they have more loosely held electrons due to their large size. Mn2 plus is much more resistant than Fe2 plus towards oxidation. So say after oxidation, Mn2 plus will give Mn3 plus, Fe2 plus give Fe3 plus. So just write their configurations. Mn2 plus, it is 3d5. After losing one electron, it is 3d4. Fa2 plus 3d6. After losing one electron, it becomes 3d5. So Mn2 plus more stable and it becomes less stable. That's why Mn2 plus from more stable to less stable, obviously it is less feasible, but Fa2 plus 3d6 less stable to more stable. So it is more feasible. You can write Mn3 plus is less stable, therefore Mn2 plus is much more resistant to form Mn3 plus. But Fe3 plus is more stable than Fe2 plus. That's why Fe2 plus, after losing one electron, it gives more stable cation. So that is more easily taking place. Next. Yes. So question is, among lanthanoids, lanthanum 3 compounds are predominant. However, occasionally in solutions or in solid compounds, plus 2 and plus 4 ions are also obtained. So what is the reason for plus 2 and plus 4 ions? So because it gives D0, D5 or D10. So you can write because of the empty, exactly half filled and fully filled electronic configuration. They can show plus 2 and plus 4. Next question. What is the reason for E0 M2 plus M for copper is positive? Copper is the only metal in the first series of transition elements showing this behavior. So what is the reason? Yes, beta. What is the reason? E0 of M2 plus M for copper is positive. So see, M copper solid to give copper 2 plus aqueous plus 2 electron. Write it in equilibrium state. So copper solid first convert into copper gas into copper 2 plus gas, and copper 2 plus gas to copper 2 plus aqueous. So here hydration energy is required, which is energy released negative. Here enthalpy of atomization is required, it is positive. Here it is sum of the first and second ionization enthalpies. So we can write that sum of the enthalpy of atomization, first ionization enthalpy and second ion enthalpy, their sum is very greater than the hydration enthalpy. That's why equilibrium shifts backward, because energy absorbed is more than energy released. So copper 2 plus aqueous form is unstable, and that's why copper solid is formed from copper 2 plus much more easily, and this is the reason why E naught of copper 2 plus to copper is positive. Next, metallic radii of the transition third series of transition metals are nearly the same as that of the corresponding members of the second series. No need to write, I think. What is the reason? Tell me. Due to lanthanoid contraction. That's it. Very good. This is due to lanthanoid contraction. Next, Explain the following. Many of the transition elements are known to form interstitial compound. Just now we have discussed that crystal lattice of transition elements can accommodate small sized atoms like hydrogen, carbon, boron, and nitrogen, and that's why they can form interstitial compounds. There is general increase in density from titanium to copper, because when we go from titanium to copper, mass increases and size decreases, and that's why density increases. Very, very simple question. Next, again, members of the actinoid series exhibit a large number of oxidation states. Same reason, due to small energy difference in 5F, 6D, and 7S in case of actinoids, and that's why they all can participate in bonding. Next question. Yes, beta. What about this? With the same D configuration, Cr2 plus is reducing, but Mn3 plus is an oxidizing agent. Because Cr3 plus is exactly half filled, T2G3, and that's why more stable. So Cr2 plus can lose electron easily. Mn2 plus is exactly half filled configuration, that is D5. Therefore, Mn3 plus can easily gain electron. Just write about Cr3 plus, that is 3D3, that is T2G3, more stable, and Mn2 plus 3D5, that is T2G3 Eg2. Just write this. That's it. That Cr3 plus form is more stable, and in case of manganese, Mn2 plus formed is more stable. Actinoid exhibit a much larger number of oxidation states than lanthanoid. Same reason. Due to small energy difference between 5F, 6D, and 7S. There is hardly any increase in atomic size with increasing atomic numbers in a series of transition elements. So when we go along the series, the increase in size is very, very less. Increase, or we can say decrease, as an atomic number increases, the increase in or decrease in atomic size is less. Why? Because, say, along a transition series, nuclear charge increases. Obviously, it tends to decrease the size, but the addition of electron is in the penultimate d shell. Penultimate means n minus 1d. That increases the screening effect, which counterbalances the effect of increased nuclear charge, and that's why atomic radius does not change much. See, this is the nucleus, these are the shells. So nuclear charge is increasing or increasing atomic number, but at the same time electrons are filled in the penultimate shell, and that's why screening increases, and therefore outer electrons are less attracted. Due to nuclear charge, they are more attracted and they counterbalance each other. Screening from the antipenultimate shell and nuclear charge, they counterbalance each other, and that's why size is almost same. Next, there is gradual decrease in size of the atoms with increasing atomic number in the series of lanthanoids. The reason is due to, this is the definition of lanthanoid contraction, and reason is, what is the reason? Due to imperfect shielding of 4f electrons due to imperfect shielding of 4f electrons. The reason is due to lengthened contraction, and this is because of imperfect shielding of 4f electrons. Next is scandium is the transition element, but calcium is not. Scandium is a transition element because it has incomplete D subshell, but calcium does not have any D subshell. Fe2 plus is much more easily oxidized to Fe3 plus than Mn2 plus to Mn3 plus. Simple, because Fe3 plus is more stable, but Mn3 plus is less stable. Means here Fe2 plus to Fe3 plus, less stable Fe2 plus is oxidized to more stable Fe3 plus. But in case of Mn2 plus, more stable Mn2 plus is oxidized to less stable Mn3 plus. That's why Fe2 plus is much more easily oxidized than Mn2 plus to Mn3 plus. Okay, so these are up to 50. So 51 we will do tomorrow. Okay, beta. Okay. So yes, beta. So today we have done up to 50 questions. This is our fifth lecture of D&F block elements. We are covering the questions from previous year as well as from the in-text of D&F block elements. In this way, we'll cover whole NCRT, its NCRT exercise, NCRT questions, NCRT in-text questions, examples, concept, and then we will do the JEE and NEET questions. JEE and NEET questions as well. So be with me and support my channel and support free education drive that I am doing from Monday to Friday. Generally, this lecture is from 6 to 7, but today we have a session from 7 to 8 because of time constraint. Anyhow, tomorrow we will meet at 6 o'clock. 6 to 7 we have a lecture. So be with me, support my channel, share with your friends, and so that our community will grow and I will enjoy teaching more students than those I'm currently teaching. That's my aim. Thank you so much to be with me and support my channel. God bless you.